Hello! Today we're going to talk about rotational kinematics. We have two goals today, and one is to simply compare straight line motion to rotational motion, particularly straight line motion in one dimension. So we've studied that, we've become experts on straight line motion in one dimension, and rotational motion looks quite different, but the equations that we write down and in fact the behavior of the system is really very similar. So we can learn a lot from applying what we learned before to this new system. And secondly, we're going to introduce a new set of variables that we will apply to rotating objects. And these are analogous to the position, velocity, and acceleration variables we used for one-dimensional straight line motion. And it turns out that those variables, like x's and v's and a's, just are not quite the natural set of units to use for rotating systems, and so we use an equivalent set that's a better fit for the rotational system. So first of all, how do we describe the motion of rotating objects, or objects that travel along circular paths? So this is what rotational kinematics is all about. It's not why it moves in this way, but how it moves in this way. So what we're going to do is we are going to start by looking at some parallels between straight line motion, one-dimensional straight line motion, and rotational motion. So what I'm going to do is I'm going to show you two things. We're going to look at a ball that's thrown straight up into the air, and we're going to compare the motion of the ball, that motion, to the motion of a disk, and the disk has a counterclockwise initial angular velocity but a clockwise angular acceleration. And if you think about it, that is in some ways similar to the ball. So we're going to give the ball an initial velocity which is directed straight up, but the ball of course is then acted upon by gravity, and the acceleration of the ball is straight down, opposite in the direction to the initial velocity. So the same thing happens with the disk. We have it initially spinning one direction, but the angular acceleration is in the opposite direction. And that makes the disk do what the ball does. The gravitational force acting on the ball eventually brings the ball to rest just for an instant and then turns it around so the ball reverses direction. The disk will do the same thing. Okay, so I'm going to show you three sets of graphs, in fact, in this simulation, and you got to think about which motion, the motion of the ball or the motion of the disk, the graphs correspond to. Okay, so think about that as you see them. Okay, so in the top left we're going to see a little movie, very simple movie. It'll show the ball going up and down, and at the same time the disk spins counterclockwise and then clockwise again. And then we'll see a graph of position as a function of time, graph of velocity as a function of time, a graph of acceleration as a function of time. Okay, so you're going to think about what those graphs are going to look like, and you really should be familiar with the one for the ball that goes up and down. We've seen those a few different times. And so let's just have a quick look at what the movie looks like. Okay, and after the movie plays once, I'll turn on the graphs one by one. Okay, so the ball again is going to be launched straight up with an initial velocity straight up, but it has an acceleration down from gravity, and it's going to rise to a height of 5 meters, and the disk is going to rotate just through an angle a little bit larger than 270 degrees, and it turns out that is in fact 5 radians, and then it's going to come back to the initial position. Okay, so let's see that. Okay, so the ball goes up in the air, the disk rotates, they turn around at the same time, they come down. Okay, so now we're going to see a graph of position as a function of time. For that, it's a beautiful parabola, and velocity as a function of time. Velocity function of time, just a straight line graph, and then acceleration as a function of time. And of course the acceleration graph is just a flat line, a horizontal line. Okay, so let's go over these graphs a little bit. So, do they correspond to the motion of the ball? Well, yes, they do, in fact. You note that on the vertical axes of all these graphs, there's no dimensions given, no units. so we should stick units on here. So if we say the position graph has units of meters, well, it's actually a very good fit to what that ball is doing. The ball goes up to 5 meters, then comes back down to x equals 0, and it does that in 2 seconds. It takes 1 second to go up, 1 second to go down. However, it's also a wonderful fit to the motion of the disk. Okay, so if we have position measured in radians, well, the disk goes from 0 radians out to plus 5 radians and then returns to 0. And so its graph is in fact identical to the one for the ball. It's just got different units. Meters for the ball, radians for the disk. How about the velocity versus time graph? Velocity versus time graph starts at plus 10, hits 0 at the turnaround point, and ends up at minus 10. Okay, if we put units of meters per second on that graph, then it's a great fit for the ball's motion. Okay, the ball's velocity is positive but decreasing positive for the first second. Then gravity has taken away all the velocity. Velocity goes to 0 just for an instant at the top of the path, and gravity keeps acting on it, and so the velocity keeps changing at the same rate and then goes negative. In other words, the ball reverses direction. And the fact that it has a constant slope, the velocity graph, is consistent with the acceleration being negative, and positive is up here. Okay, so that's a great graph, velocity versus time, with units of meters per second for the ball. But it's also a wonderful graph for the motion of the disk. If its angular velocity is a function of time, angular velocity measured in radians per second. The disk starts off with a counterclockwise velocity of 10 radians per second. There's something that acts on the disk that is giving it a clockwise angular acceleration, a constant clockwise angular acceleration, and so that angular velocity comes down at a steady rate, reaches 0 just for an instant at the turnaround point, and then goes negative. And then if we look at the acceleration versus time graph, we're approximating the acceleration of the ball as minus 10 meters per second squared. But that graph also is a good fit for what the disk is doing if we give that graph on the y-axis units of radians per second squared. Okay, it's got a steady angular acceleration of 10 radians per second squared directed clockwise, and counterclockwise is our positive direction for the rotation. Okay, so the neat thing is the graphs can fit either the one-dimensional straight line motion of the ball or this rotational motion of the disk. Okay, so same graphs. So we really do see the same kind of physical behavior of these two systems, which really are experiencing different motions, up and down or around and back. Okay, so let's consider this very long question. So if you take that disk that we just looked at and choose a point, not the center but some other point, on the disk or on a wheel, on any wheel that's spinning. At a particular instant in time, are there any other points on the wheel that have the same speed as that of the first point, the one that you chose in the beginning? How about this? At the same instant, are there any other points on the wheel that have the same velocity as that of the first point? Okay, so think about these four answers and choose the best one. 1, plenty of points with the same speed and plenty of points with the same velocity. 2, plenty of points with the same speed but no other points with the same velocity. 3, kind of the opposite of that, no other points with the same speed but plenty with the same velocity. 4, no other points with the same speed and no other points with the same velocity. Okay, so which answer do you like the best? Spinning disk, say, imagine a two-dimensional system like a spinning disk. Pick a point, choose any other point. Can you find a second point which has the same speed or same velocity as your first point? Okay, so here's a spinning wheel with or spinning disk with 5 different points labeled. Okay, and these red arrows represent the things spinning counterclockwise. So the red arrows represent the instantaneous velocity of those points. The velocity vector is tangent to the circle that the points are spinning in. Okay, so one thing to notice is the velocities are all different. Okay, so every point on the wheel has a unique velocity. However, there are points which have the same speed. If you look at the 2 points halfway out from the center to the outer edge, there's 2 points on that same circle. One above the center, one below the center. And they have the same speed. Their velocities are different because the velocities are in opposite directions, but the speeds are the same. So, what do we learn? Is there any point on the wheel that has the same speed as the speed of another point? Absolutely. All points at the same distance r from the center. Same distance from the center, which we call r. How about velocity? Any other points on the wheel that have the same velocity as that of the first point? And in fact, no. Okay, so same speed, but different direction of the velocity, so different velocities. So all points have a unique velocity on this two-dimensional spinning disk. Okay, so let's consider this some more. Now, something's got to be the same. So we'll take those same 5 points, and one thing to notice here is if we pick an eighth of a circle that they spin in, okay, so they all rotate through an eighth of a circle in a particular time. Now they're going through, their path lengths are different for the most part, because most of them are different radii. The two that are at the same radius have the same path length. So even though every point has a different velocity, every point in fact has the same angular velocity. So all these points have gone through 45 degrees in whatever time it took that wheel to spin through 1/8 of a circle. Okay, so that's the same angular velocity. If it took a second to go through 45 degrees, then their angular velocities are 45 degrees per second in a particular direction, which we could say is counterclockwise in this case. Okay, so now we've invented something we call rotational variables here. So we saw that velocity doesn't really fit here. Every point on the wheel, how many points are there? You could split that thing up into a million, a billion, a trillion, however you want. We'd have a million, billion, trillion velocity vectors, all different. But there's only one angular velocity for the whole system. Every point has the same angular velocity. Okay, so this is why we define these new set of variables, so we don't need to keep track of a million or a billion or a trillion things. We're just trying to keep track of one thing. Okay, so here are the variables that we use when we're talking about rotating systems. And there are ways to transfer back and forth between rotational motion and straight line motion, and we'll do that, but let's just go over the rotational variables we use, and these are analogous to what we did for straight line motion. Straight line motion, we had position, we had displacement, we had velocity, we had acceleration. Okay, so for a rotating system, we have angular position, which we usually measure in units of radians, and we use often the Greek letter theta to represent the angle. And remember that pi radians is 180 degrees. Okay, so it's 2 pi radians all the way around once. Pi radians is half a revolution. 360 degrees is, of course, a whole revolution. And 1 radian is something like 57 degrees. Okay, just for a reference point. Then we could talk about angular displacement. Well, what was displacement? We said we have x's measuring positions, we have delta x's measuring displacements, so we have angular displacement, which is about 45 degrees for the displacements, angular displacement shown in the picture. Then we have angular velocity. And this thing looks like a W, but is in fact the Greek letter omega. It's the little thing that looks like a curly W. And omega is the rate of change of angular displacement. Rate of change with respect to time. Okay, so we have angles and thetas in units of radians, then our angular velocities are in units of radians per second. Now this is a vector. Note that all these things are vectors, these angular displacements and angular velocities. So in this case, if we're all looking at this from the same perspective in front of our screens, looking at this, then we can say the angular velocity is directed counterclockwise. So we can often give directions in terms of clockwise or counterclockwise. Now in fact, the true direction of the angular velocity is given by something we call the right-hand rule. If you take your right hand, curl your fingers the way the object is spinning, so you hold your right hand up to the screen, curl your fingers counterclockwise, and hold out your thumb. This is on your right hand. That's why you call it the right-hand rule. Your thumb points out of the screen. So the angular velocity vector, in this case, is directed actually out of the screen. But we'll often be able to use clockwise and counterclockwise. So don't worry about that too much. And finally, we had an acceleration for straight line motion. So we have the equivalent, the rotational kind of equivalent, which is angular acceleration. We use the Greek letter alpha to represent that. And alpha is a vector. And it is the rate of change of the angular velocity, delta omega over delta t. And now we have units of radians per second squared. Okay, so if the object is rotating at a constant rate, angular velocity is constant, then the angular acceleration is 0 because there is no change in angular velocity. So note that it's not omega over t, it's change in omega, change in angular velocity over a time interval during which that change might occur. If there is no change in angular velocity, then your angular acceleration is 0. You only have an angular acceleration if the object is speeding up or slowing down as it rotates. Okay, so let's in fact talk about speeding up versus slowing down. Okay, so I'm going to pick a point, and in picture A, I've got my disk rotating counterclockwise, and in fact it's going to be speeding up as it goes counterclockwise, so it has a counterclockwise angular acceleration and a counterclockwise angular velocity. Now, in fact, if you get out your right hand, you realize that both those vectors are in fact out of the screen, but let's just talk about clockwise and counterclockwise for now. Okay, so that point in red to the right of the center has two different accelerations. Okay, it has both a centripetal acceleration because it's experiencing circular motion, and it has a tangential acceleration because it's speeding up as it goes around the circle. Its speed is increasing. So our centripetal acceleration is our traditional v squared over r, which we can write, remember, as omega squared r. So that actually increases as omega increases. And if omega doubles, then it increases by a factor of 4. Okay, fine. And the tangential acceleration is what is connected to the angular acceleration. Okay. So AT happens to be r alpha. So if you take units of meters, that's what r is measured in, by units of radians per second squared, you end up with meters per second squared. So the radian is kind of a funny unit. We kind of put it in or take it out as is convenient. Okay, in some sense it doesn't really count as a regular unit. Okay, so our acceleration, our tangential acceleration, tangent to the circle, does not have units of meter radian per second squared, it's just meters per second squared. Even though the angular acceleration we can write as radians per second squared, or if you want, just per second squared. Okay, in the bottom picture, we have the same omega, the same point, but the difference is that this disk is slowing down as it rotates counterclockwise. The top one was speeding up. Okay, so at that instant in time, we have exactly the same centripetal acceleration if we have the same omega, so we still have omega squared r, but that would be decreasing as time went by because the alpha opposite in direction to the omega makes the disk slow down. And if we turn alpha around and face it the other direction from what we did at the top of the screen, then AT, the tangential acceleration, also goes the other way. Okay, so the alpha and A tangential go together, but they're not directly connected to the centripetal acceleration. Okay, so we're going to look at a lot of different analogies. This is only the start of all the analogies we're going to look at between straight line motion and rotational motion. Okay, so here's a nice table that kind of summarizes some of those analogies. So we have variables of position, velocity, acceleration. For straight line motion, we use variables that often look like x, v, a. V is delta x over delta t, a is delta v over delta t. The equivalent rotational motion variables are, instead of x we have theta, instead of v we have omega, the angular velocity, instead of a we have alpha, the angular acceleration. They're connected to one another. Theta, omega, and alpha are connected to one another just like x and v and a are connected to each other. Omega is delta theta over delta t, where v is delta x over delta t, etc. And the straight line motion and rotational motion variables are also connected to each other by, in general, factors of r. Okay, so if you're out some distance r from the center and you go through 45 degrees, 52 degrees, whatever, you take your angle in radians, have to be in radians. Okay, if you multiply by r, you get the length of the arc that you moved along. Okay, or if you take the arc length, which is x in this case, divide by the radius of the path, you get the angle in radians. If you skip down to the bottom, we've actually already seen this relationship between alpha and a, and it's the tangential acceleration that it's connected to, alpha. So alpha is the tangential acceleration over r. And there's a similar connection with omega and v. Take the tangential velocity, divide by r, and that is in fact your omega. Okay? And we had a whole nice set of straight line motion equations, constant acceleration equations. So we can just replace x's by thetas and v's by omegas and a's by alphas, and we're going to get a nice set of equations that works for rotational motion. Okay? Oh, and once again, remember the t in those equations stands for tangential. Okay, so here are three of those lovely straight line motion equations that we used for one-dimensional motion, and we also used them for two-dimensional motion because we split 2D motion into two one-dimensional motions, of course. And then we have our equivalent set for rotational motion, and again these work as long as the angular acceleration is constant. So the equivalent of velocity is initial velocity plus acceleration times time is angular velocity is the initial angular velocity plus the angular acceleration times time. X position is initial position plus initial velocity times time plus 1/2 acceleration times t squared. Equivalent equation for rotation. The angle theta is the original angle theta, initial angle theta, plus the initial angular velocity times time plus 1/2 alpha t squared. Okay. How about the bottom one? V squared is V initial squared plus 2 alpha delta x. What does that mean? The speed, the square of the speed at some point in time is the square of the initial speed plus 2 times the acceleration times the displacement. The equivalent equation for rotation is the angular speed squared is the initial angular speed squared plus 2 times the angular acceleration times the angular displacement, the angle the object went through. Okay, so we're going to use those and get the be able to use lots of get a lot of mileage out of those equations, just like we got a lot of mileage out of the straight line motion equations. Okay, so anyway, our theme for today was hammering home just how similar rotation is to straight line motion. Okay, they might look completely different to you, but the physics is really all the same. The same kind of equations, and we treat these systems in a very similar way in our analysis. Okay, so I think that is all for today. And before we go, don't forget, this was very important for straight line motion, use the appropriate plus and minus signs for your V's and A's and X's, just like you do for omegas, alphas, and thetas. Think about your signs. So pick a positive direction and see which way your different variables go compared to that positive direction. Okay.